Last topic. What about heteronuclear diatomics? So there is more to life than homonuclear second row diatomics. Now for this class, as far as we're going to go is heteronuclear second row diatomics. So as an example, nitrogen monoxide, NO. So if the elements are different, but they're still both second row elements, the energy level diagrams look for the most part similar. Now, one big difference is that the energies of the starting or the original atomic states are different. And generally the rule is that the heavier element has lower energy. These energies are lower for the heavier element. Which means that that this is nitrogen and these would be the oxygen atomic orbitals. But that really doesn't mean much. The molecular states in the middle look exactly the same, and for heteronuclear molecules, it is always this configuration where the pi states are lower in energy than the sigma 2p state. So NO, so let's count. So this is one of those weird things, one of those weird molecules that actually has an odd number of electrons. You get 5 in from the nitrogen, 6 in from the oxygen, giving us a total of 11, and we can just populate. So again, the Lewis structure for this again has a lone dot because it's an odd number. So one here, one there. So we're up to 4, 5, 6, 7, 8. You note in this case it was animated correctly. 9, 10, and lastly 11. So this gives us a bond order of 2.5. This is a half integral bond order, and that's okay. There's nothing in molecular orbital theory that says that electrons have to exist or be shared pairwise. And in fact, anytime that you have an odd number species, you will get a half integer bond order, 2.5. And the electron, so let me ask you this now. Take a look at what we have here and tell me which would you predict has a stronger bond, NO or NO+. So hit pause, think about that for a minute. And what you want to look at, there's a couple of things. They're all kind of related. Basically what matters is for the strength of the bond is the relative numbers of antibonding electrons and bonding electrons, or the bond order, which is which tells you about the difference between those numbers. And so how's that going to change going from NO to NO+? Well, you have made a positive ion, so you're going to lose an electron. Okay, and you're supposed to lose that electron, so let me do that. Bye. So that one goes away. And the important thing is that we have lost an antibonding electron. So the number of antibonding electrons has gone from 3 to 2. The number of bonding electrons hasn't changed. So the bond order of NO+ is 3. And from that, you can take that NO+ actually has a stronger bond than neutral NO does. In fact, it's a very strong one, almost, again, comparable to a triple bond. All right, and I want to do one more example for a heteronuclear diatomic, and that is so the next example I want to do here is carbon monoxide. Again, so heavier element, lower energy, so the orbitals on the states on the left here in this case would represent carbon, states on the right would represent oxygen. And because it's a heteronuclear molecule, we've got this ordering here with the pi 2p's lower energy than the sigma 2p. Count the valence electrons. In this case, we got 10. And so just put them in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what's our bond order here? So try to figure, work that out if you will. All right, so we've got 8 bonding electrons. So we've got 2 here, 4 here, bringing us up to 6, and these 2 can bring us up to 8, and just these 2 here for the anti-bonding electrons. Gives us a bond order of 3, and this is consistent with Lewis theory, where if you were to do the correct Lewis structure for carbon monoxide, you do predict a triple bond between the two. All right. And one thing I want to show you is these are kind of pictures of what these look like. For carbon monoxide in particular. And one big difference here is that these are not symmetric anymore, like they were for the homonuclear diatomics. And in particular, there's one thing to note here, that in the bonding configurations, like this one here, there's more electron density around the oxygen. Now, between carbon and oxygen is more electronegative. So we've got electron density around the more electronegative element. This is a good thing. And you see it in this state here as well. But now let's look at the anti-bonding configurations, like this one right here. You actually have greater electron density around the carbon atom, the less electronegative of this pair. Same thing for here, and actually the same thing for here as well. This is not a good way to distribute electrons in space, which is why those are anti-bonding configurations. So the lower energy states for the homonuclear diatomics have a little more electron density around the more electronegative element. So I just wanted to show you that. So let's review what we talked about here. You should be able to kind of roughly sketch the orbitals if I ask you to kind of see what they add up to. As far as to make these crude pictures here, the same color overlap, join them together, opposite color overlap, split them apart. Give me electron configurations for a molecule, give me the bond order, and tell me if it's paramagnetic or diamagnetic. And that is our molecular orbital or molecular electron state theory. And with that, we have finished the content for Chem 1215, so congratulations. I am sorry we couldn't celebrate together face to face, but pat yourself on the back, kind of give yourself a woohoo and cheer because that's the content. All right, see you in Zoom.